Hi, in this particular video we are going to explain over the concept of sigma. Now as you have seen that I have written this letter, this is a Greek alphabet and this is the capital which is called the sigma. So in this video what we are going to do is that we are going to look forward for these few points. What is sigma? That is what this sign is all about. How can we use sigma? That means this is a mathematical operator which is used widely in mathematics. So how we can use this sigma? What are the useful methods? Definitely there are certain useful methods of using sigma. So we are going to look forward for that. And we are also going to look forward what is the difference between summation and integral, which is going to be the last part of my video. So now that you have seen that I have written something, this letter, which is a Greek alphabet, and there are some indices below and at the top and on the right hand side. So we will start explaining what is that sigma is all about, how we can use this notation or the operator, what are the methods, and at the end the difference between summation and integral. So this is a good point to start. So we will start with what is sigma. Now we have seen that sigma is actually a Greek alphabet, which is the 18th alphabet which comes in the Greek chronology of alphabets. So we have got in Greek, let us see if we can write them. The first what we have got is alpha. So I am writing the capital ones. So we put it as A, as alpha. Then we have got beta, that is B. Then we have got gamma, which is written in this way. This is gamma. Then we have got delta. Then we have got delta. Then we have got what is called epsilon. Epsilon is written as E. Then we have got what is called a zeta. We have got zeta, so we write it just as Z. Then we have got the alphabet which is called eta, which is almost similar to the H. Then we have got eta, then comes the theta. So these are all capital letters, so we put it like this. After the theta comes iota, which is I. We write it as I. After iota comes kappa. After iota comes kappa, which is K. After kappa, the next letter comes is lambda. Lambda, which is written like this. So it is this. This is lambda. After lambda, which comes is mu, which is just like English M. After that, the next letter which comes is nu, which is like English N. After that comes Z, which is written like this, this and this. This is Z. After that comes Omicron, which is O. And then comes pi, which we are quite familiar, which is written like this. After pi comes rho, which is written like this. And then comes sigma, which is written something like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is the 18th letter in the Greek alphabet. Now we have, as like in English, we have capital and small. So we have a capital sigma, which looks like this, which we are going to use in this video. And we have a small sigma, which looks something like this. So this is the capital, this is the small. Now let us see that what is the usage and why do we use sigma. Suppose that we have a summation of letters. Say for example, if we have got 1 plus 2 plus 3 plus 4 plus 5. And in this way it goes on dot 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 till plus 10, right? So how we can write it? The basic idea is that if you are going to write this series 1 plus 2 plus 3 plus 4, it takes a longer space, right? And it looks cumbersome also. So in that case, can we use this sigma notation to sum it up and write it in a much more cleaner way? So this particular from 1 to 10 can be written in this way. We can use this. So we write sigma, right? Then we use an indices. Indices are those which are varying. So generally it can be used as M or K or N, anything. But currently what I am doing, I am using I equals to 1. That means it will start with 1. Then on the top of this sigma, we write something which is called the which is called the end part. So we are ending at 10. So we put a 10 on the top. And then we write an operator which is I. Now, for example, if we go forward and we want to write this part, so what we do is that we write 1 first, that is the first part, right? This is, so we put it here 1. This is the 1. So we put the first part as 1. Then we increase the indices by 1. So I plus 1 equals to 2 plus 3 plus 4, and it goes on till plus 10. So this is a much more neater way to explain or write about the entire series. So it is simple. We write the sigma first. We put the indices I or M, whatever you want to mention. We put 1 at the top, that is the starting one here, till the end equal be 10 and times I, that is, this is the operator which will go on. This particular I, which I have written over here, it will go on changing as we proceed with the video. Now, for example, I want to write it again with a similar kind of an example. I want to write I, this is 1. Say, for example, if I want to write to 1 plus 2 plus 3 plus 4 dot up till plus 100, right? So this is a sum which I am going to write till 100. So let us see how we can write it. You can use it, you can pause this video and you can try it yourself. This would be something like this. Similar, we will put it as sigma. We put it as sigma. This is a capital sigma we are writing. What we have started with I equals to 1, right? And it is going till 100 I. Remember that this indices which is mentioned right at the bottom should be equal to this. If you're writing I, it should be I. If it is K, it should be K. Don't mention I over here. This is I believe you can understand. Yeah, little dot. So it is not that you write I over here and it's K over here. This is again equals to 1 plus 2 plus 3 plus 4 dot till 100. So this is a much more neater, simpler, and I would say a different way of writing things. I will say a coincised manner in which we can write things. Let us see another example of this. What if we are doing this part? Say, for example, we write sigma of I equals to 0 and it goes up till 50. And we have an expression which I called it as pi I squared. Pi I squared. So what I will write, what I will do is that I will put a pi over here, right? We start with 0, so I put 0 over here. It is squared, so I put it a square. Plus, I again write pi, which is a constant. Instead of 0, it is incremented till 1. So what I will do is that I will write 1 squared. Plus, again I will put pi, and this is the second, 0, 1, then it will be 2. It will be 2 squared. Plus pi 3 squared, and it will go on till plus pi 50 squared, right? So these are the different ways in which we can write the value. So what we have done, you see, I have mentioned it as 0 and is going up to 50. Here we have mentioned it I going up to 100. Here I have mentioned I going up to 10. And it can be anything. So you see that when I'm writing this part, say for example, let me rewrite it for you. So we write it as pi, right? I equals to 0 till 100 pi I squared, right? So you see this is a much cleaner way, and it is a coincised manner in which we can express these areas, right? This reminds me of before we go forward with this proceedings, this reminds me of a very famous joke. It's called a mathematics joke. So let me just share it with you. If we take 3 values, say for example, I take root of 1, and I take 2 cube, and I take sigma, and I take pi. So we can rewrite it as, we know root over 1 is called I, and then we can write this 2 cube as 2 cube, okay, I, This is how much? 2 to the power 3 is 8. So I can write it as 8 ATE. This is sigma. So we can call it as sum, right? And this is pi, which is called a pi. So I ate some pie, right? So I ate some pie. That means I have eaten something. Maybe it is cake or pastry or whatever, and it is delicious. So just to share with you a very common joke, root over 1 is I, 2 cube is 8. We can call it 8 some pie. So I ate some pie. Now let us see a very common expression which we can reuse in different ways in mathematics. And this is something I would like to say it is a common thing. We have generalized these things. So let me write it. So we can now write, I'm writing it in a bigger fashion so you can understand. This is sigma. We put it as k equals to 0. That means this can be 0, this can be 1, 2, minus 1, minus 4, doesn't end. And I put on the top the n. So I can write over here, for example in blue, this would be the starting part. So I put it as start. This would be the ending part. That means my last part, what it would be. And I can put it as x times k. This would be the expression in which we can do numerous permutations, combinations, whatever the way that we want to do. So as you see that this is something which we have written in a more generic manner, right? This is sigma, this is start, this is the ending, and these are the expressions which will carry on. So let us see one example, right? So what we do over here is that we take an example where we write it as a sigma k equals to 0 right at the bottom. That means k starting from 0 till 4 k squared, and we will see how it happens. So we put a 0, right? 0 and it is squared, so 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared. We have to stop at 4. Why? Because the upper limit is 4, so we stop at 4. So let us see how much it comes. 0 plus 1 plus 4 plus 3 square is 9, 4 square is 16. So how much? 25, 29, it comes to 30. So this is the value, this is the answer given to it. Let us see if we can solve a further example, and in this case we will put it a little bit different. So we put it in this way. We put it as sigma, and we write n equals to 0. We put a different indices over here, n equals to 0, and we take the top, we make it as 4, and here we write minus 1 to the power n, that is nth power, whole divided by 1 plus n. This is the expression. So what we are going to do is that, let us see how we can we can solve things out. So what we do in the top is that we put minus 1, right? So the first one would be 0 to the power 0 whole divided by 1 plus 0. Then we proceeded further, that is minus 1 to the power 1 whole divided by 1 plus 1, plus I am expanding this series. So minus 1, the next power is 2. We take it as 1 plus 2. Then we forward plus the third one, that is 1 minus 1 to the power 3, 1 plus 3, and we will stop at 4. So plus minus 1 to the power 4, that would be 1 plus 4. So this is the general series that we have got. So how much we get it? So 0 to the power 1 is 1, 1 by 1 plus 0, that would be, this will be 1, 1 plus 0, 1. Plus minus 1 to the power 1 would be minus 1 whole to the power by 2. Then we get minus 1 squared, that would be plus 1 by 3. Then we get for how much? This is minus 1 to the power cube will be minus 1, 4. Plus minus 1 to the power 4 would be again 1 by 5. This is the series that we get. Now what we can do is that we can quickly convert it to the common numerator and denominator. So for example, I make the denominator all same to 60 plus 60 plus 60 plus 60 plus 60, right? And what I get on the numerator is 1, so 60, 60, this would be minus 30, 60 by minus 2, yeah. So this would be 20, this would be 15, minus 15, and this would be 15, 5 12s are 16, 60, so it would be 12. So eventually my result would come to 47 by 60, and this is the answer for this sigma notation once we expand it. Okay, so far so good. What we will do in the next part is that we will look forward for another interesting feature. So I think by far things are pretty clear. You can see how things are proceeding. We have expanded sigma. We have seen how we can start and how we can end with. So what we do is now is that we take another expression. Say for example, if we start with this particular expression, okay. So we see over here, we take another expression. Say for example, I take it as sigma I. We start with the value of I equals to 4. Right, and at the top what we do is that we take it till 12. Now you see, if I want to expand this part, and this is I, right, now what we do is that we mention it this as, you know, it would go on, it would start with 4, so it would be 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12. So it will go on till 12, right? And we can find out through calculator, otherwise the sum is 72. Now what happens is that if we take this kind of a sum which will go on till 50, 1 plus 2 plus 3 up till 50. So what we can do is that we can write sigma of I equals to 1. We start it with 1. We go till 50, right? We go till 50 and it is I times. So let me write it for you, just up till few numbers. So what we get is 1i plus what we get 2, okay, then we get 3, then we get 4, and dot till 50, right? Now you see an interesting feature that if we want to add these things up till 50, now if I write it in a reverse way, that is from 50 I'm coming towards this, so I put a 50 first, then I put a 49, then I put a 48, then I put a 47, dot it goes on, and I reduce the value till 1. So 50 plus 1 you see is 51, 49 plus 2 is also 51, 48 plus 3 is also 51, 47 plus 4 is also 51, and 50 plus 1 is also 51. Now what we have seen over here is that let us write this in a different way. Okay, so what we do is that we write this sigma notation. So this part I can split it in two parts. So one is that I can write this plus I can also write this as sigma, okay, 50 I equals to 1 times I, right? And if I expand it, say for example this part, and I multiply both of these by 2, so I get something, let me rewrite it for you. So if I multiply by 2 on both sides, so I get 2 sigma I equals to 1 till 50 times I, okay, times I, whole divided by 2. I'm dividing the entire thing by 2, and what I get over here is that I get 50 times 51. So I can obviously write 50 multiplied by 51 whole divided by 2. This 2 and this 2 gets cancelled out. This 2 and this 2 gets cancelled out. And what we get over here is this. We get sigma I equals to 1 till 50, right? Okay, times I equals to, if I solve this out, so I get 25 multiplied by 51, which gives to 1275. Okay, so that means this can be carried on for any number. It can be carried on for any number. It can be for 10, 50, 100, 1000. It can be for any number. So what we get over here, let me rewrite this for you. It looks a little bit cumbersome. So what we get over from here is that if I write this sigma and I equals to 1 till 50, right, times I equals to 1275, right? So we wanted to make it this way. So this would be the value of I times equals to 1275. So in order to make it in a more generic way, which is a very useful formula, which we mostly use all throughout our mathematics. So let me write it for you. So here we go, sigma I equals to 1 till n. So n is anything, 500,000, whatever, times I equals to n, which is the first one, that is 50, okay, multiplied by n plus 1, which is 50 plus 1, which gives us 51, whole divided by 2. And this is a very important formula in sigma. This is very important. So you see that what we have done is that if we want to take further summations, which would be going on from 1 to 50 to 100, etc., we get this formula. So we get n multiplied by n plus 1. So we get exactly 50 plus 1 whole divided by 2. We get the final result as 1275. We will look forward for another example where we are summing up something like this. So we write over here sigma I equals to 1 till 25, but the expression over here will be I plus 2, right? So we are going to solve this thing out. So what we can write here is that it would be equal to, we can split these things to in different ways. So we put a brace, and what we can write over here is that we can write sigma I equals to 1 till 25 times I, right? This is 1, plus what we can do is that we can write within braces sigma I equals to 1 to 25 times 2, this one, this 2. Now if I write it in this way, what we will get is that it would be equal to 25. This we get it from this formula, n into n plus 1 by 2. So we put it as 25 into 25 plus 1 divided by 2, plus what we get over here, this is 25. So we get 25 multiplied by 2, right? So what we get, it's quite simple now to solve. So if you solve it over here, 25 times 2 would be 50, and this would be 26 multiplied 25, this would be 325, and the result would come to 375. So this is a nice way in which we can expand this sigma into two parts. One is this one I, and we take 2, and in this way we can find out in a much more easier way what things would be. Now let us proceed to a typical example of sigma in which we get a kind of a different expression. What is that? Say for example we want to we get an expression something like this. So we get sigma, and we start it with k. Let us now take it from I to k. K equals to 1, right? And we proceed up to 4, and here is an expression which is called 3k, right? So this is something which we are going to solve. Now say for example what I get is that I get 3 times 1. This is starting with 3, right? So 3 times 1, so 3k, this is the constant, plus I get 3 times 2, plus I get 3 times 3, plus I get 3 times 4. Now note one thing, which I'm going to write it in different colors so that you can understand. What we see over here is a factor of 3. Do you see 3, 3, 3, 3? 3 is common. So let us take 3 outside the bracket, right? And let us write 1 plus 2 plus 3 plus 4, right? Remember that we are not concerned about the answers. That is why I kept it pretty simple, like for like anybody can do, like my daughter can also do it, but most important is the method. So what we get, 3 multiplied by 10 equals to 30. Now you see one thing what we get. We started with this, what we are getting. So we can generalize this thing. So we get something like, we can write this part, this one, let me put an arrow. So we can write this part as taking 3 sigma Okay, k equals to 1 and it goes up to 4 times k, right? So let me write it again for you because you won't be able to see this part. So we get it as 3 sigma k equals to 1 up till 4 times k, right? Now generally this part, this entire part, we have taken this outside. We can even generalize. So we are going to generalize this one. So what we get from generalization is that we can write it in this way. We can write sigma, okay, let me write it over here, you can understand, yeah. Sigma of k equals to 1, and it goes up to n. So it is not 4, it can be any number. So let me put it as n. C, that is the constant, times k. That looks much more cleaner. C is the constant. What is the constant? So we got what? C, number 3. 3 is constant and k keeps on varying, 1, 2, 3, 4 and so forth, right? So this can also be written something like, say for example, if I write c times 1 plus c times 2 dot 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 till c times n plus c times n, right? So this is actually something. So if you get a sigma of c times, so if you get sigma of c times of a variable where k, or variable k, this is k, where c is a constant, then we can use this part, which is a much more generalized way of writing k equals to 1, and it goes, and we take this c outside, right, and we put it n times k. So there you go. This is the value. So what we have done is that we have taken c outside the sigma. We have taken c outside the sigma, and it varies from k equals to 1 till k equals to n and times k. So obviously c will always be repeated, that is this part 3, right, and it will go from 1 to up till n times k. So remember that if you get sigma of c, that is a constant, times a variable, which is this one, 1, 2, 3, 4, you can take constant outside. This is where you have taken constant outside, and this would be the sigma notation, which is sigma 1 till n multiplied by k. So this is another important case. Now I have to pause my video right now because I have got further examples, special cases to show, because this video is getting a little bit longer. So let me quickly summarize before I put a pause to my video. So what we have learned from here is that 18th letter of Greek is sigma. The capital sigma looks like this, small sigma looks like this. It is basically meant to summarize things, summarize 1, 2, 3, 4, 5, and it can be written in a much more neater way. This is the starting zone, this is the ending zone. The expression keeps on changing and changing. So we have seen few examples, k equals to 0, 4 and times k square, how it looks, minus 1, how it looks. And also what we have seen over here is this. If we are getting something like we have to add up 1 till 50, how we are going to do it. We are got a formula which is n multiplied by n plus 1 times t divided by 2, so through which we can use any formula or any calculation. It can go up to 50,000, any up to n. We have also seen that if we get a typical kind of a case where we can solve things out, if we get a constant or something like this, no, I'm so sorry, yeah, this is something which we have solved, like splitting this sigma notation into 2 parts, right? Also what we have seen is that if you get a typical expression where there is a constant, then we can take the constant outside the notation of sigma, and which we have written as 3 times k. If we generalize, it becomes c 1 to n times k. We are left with few more sigma notations which I am going to explain. So I think that we have covered up till this part. That is, what is sigma, we have known. How can we use sigma, we have come. This, some useful methods is still going on. So hold on till my next video, in which I would be explaining further on the methods and some typical cases and examples of sigma, and then we are going to look forward for the last part, which is very conceptual understanding difference between summation and integral. Don't worry, I won't be dealing with calculus, but just intuitional understanding. Hope you liked my video. Watch out for the part 2 of sigma. Thank you very much.